I'd like to first thank Dr. Dipankar Pal and Dr. Youngyu Lee and Soma for giving me this opportunity. I'd like to also thank the audience to join this meeting, even in the evening of American time. So it's my privilege to share what I have done recently regarding data-driven design for materials, structures, and process design. Okay, so let me start. So this is the today's contents. So these are like 5 topics that I prepared. So because I found that the audience will have a quite wide background, I will briefly talk about the role of AI, which is the fast and accurate inference. And then after talking about AI, I will talk about how to utilize AI for the design of materials, shape, and the process. So I'll divide the problem into 4 categories and giving you like a very overall and holistic view of the design approach. And then I will come up with some Ansys software design example. I just prepared this for past 3 weeks to prepare for this meeting. So I'm going to show you some example with Ansys and just to discuss about some suggestions from users side. And then I'll talk about like how to optimize with a small and costly data set, which is related to guiding experiment or simulations with a multi-objective target. And as a final topic, I'll talk about introductory homogenization, which can be used for scale bridging of particle reinforced composites. Okay, so these are contents. So before starting the core contents, let me start with my self-introduction. Yeah, so this is my research group. So I have like about 2 dozen of students, and I got my degrees in physics department around like 12 years ago, and I joined KAIST in mechanical engineering about more than 10 years ago. So it's been like 10 year and a half in KAIST Korea. So, and this is overview of what's going on in my lab. So in the first 3 years of my career, I focused on nanocomposites and nanomechanics because I got my PhD degree in molecular dynamics and nanomechanics. And then the next 3 years, I expanded my research to more like a continuum simulation and continuum theory, because Korea has a huge and a strong manufacturing industry. I found that to make some impact in Korea, I have to expand my expertise into continuum theories and simulations. And for the past 4 to 5 years, what I have done was combining the data set from simulation theory experiments with AI model. I apply this to design of materials, structures, and process, and some pattern analysis. So this is like overall activities in my lab. So regarding the first 4 or 5 years of focus, it was like AI for the manufacturing. So to develop a product, we have to develop materials and shape and structures and processes. Although at a first glance, they look completely different problem. In terms of data input and output, input is black and output is this orange one. It's like, similar and universal way of applying data analysis. So the questions I have asked regarding these 3 aspects was, what will be the challenge and opportunity of AI? What will be the proper choice of AI model in the plethora of AI papers? And the second question I also had in collaboration with manufacturing companies in Korea was, is deep learning always useful in engineering application? So one of the AI application example that I'm gonna show you today is like a semiconductor ALD coating chamber shape optimization. So I happen to work with some company. This company is owned by Samsung's founders' first daughter's family. So what they had some difficulty was because they had some difficulties in controlling the flow uniformity. And because of this flow non-uniformity, they have some coating non-uniformity in ALD coating. So what we have done was using Ansys tool, we try to generate a lot of data, and we are able to generate a shape that can generate flow uniformity and also resulting in coating uniformity. That's one of the application. And another industrial application can be collaboration with Hyundai heavy industry. So in building huge ships in Hyundai heavy industry, what they need to do is they have to like bend and twist a large steel plate in a target. So what they have done until now was they collaborate with field experts with like a 20 years or 30 years of experience. And these field experience expert shows the shape of a steel plate and shows the target bending and twisting angle. And they suggest induction line heating pattern such that to satisfy and bend the steel plate in this way. However, once these like old gentlemen get retired and it's not easy to make a knowledge transfer, what Hyundai Heavy Industry is doing is they want to, convert these expertise into like an AI model. So now, in collaboration with the Hyundai Heavy Industry, without the help of this field engineer, we are developing a way of suggesting induction heating line to satisfy bending and twist angle required to match the shape of the ship. And yeah, these are some examples like plastic design and heat management system and like a leaf pattern optimization and some flow control devices. As I told you, I will touch on like injection molding process. These are some industry applications I have done for past 5 years. So in my lab, like these are like the overall simulation and theory capability, like a multi-scale modeling and fatigue and multiphysics. I'm trying to implement these into the umbrella of Abacus. And the main topic of today will be like this kind of a thing, like optimization in like 4 different categories. And for the details, yeah, you can find the overall holistic picture from this paper. And these are related to data-driven prediction and classification. And some examples of each case can be found here. Okay, so this is like some self-introduction. So let me move on to the role of AI. So if I can say just in one word, it'll be just fast and accurate inference or prediction and classification. So yeah, if I just define AI system, it'll be just a combination of various AI models such as ANN, support vector machine, and decision tree, and etc. And what AI model is doing is it use data set in the terms of like image, time series, and numerical and categorical data set, and try to learn the patterns within this data set. And if I map this into more mathematical perspective, it can be written as this. So here, the domain and codomain can be numerical, categorical, and image and time series data. And AI model is, what AI model is doing is find the mapping f that from the domain to range. And when the range is continuous, we can call that as like a typical regression. If this is discrete, we can call it as a classification. So if we train the AI model properly, we can deduce this f, which is quite intricate patterns beyond the human recognition. And second, we can predict and classify at like a speed over 100 times or 1,000 times quicker than computational simulation. So related to one, because we are finding the relation in the data set, it's really important to secure quality data set because garbage in will result in garbage out. And second thing, although we train the AI model that predict and classify very fast, yeah, we have to devise an efficient way utilizing this superior inference of AI. So yeah, one of the example of AI can be like starting from this image of like a binary composite plate under tension, like a tension in vertical direction. We can generate stress strain curve. Now, after collecting big data and training AI model without running FEM simulation, we can predict stress strain curve out of this image only. So this is image to numeric array paper, which is cited quite many times. And second example is, if we measure like strains at a few points within a surface, out of this number information, we can predict entire surface strain distribution image that can be generated from digital image correlation, which is quite expensive apparatus. So this is like an image to number prediction. And one of the example that I also want to show you is like replacing FEM. So if we run like a FEM simulation of this crack propagation, if we just train AI model properly, yeah, without running FEM, we can predict stress distribution and the correct phase field propagation using deep learning model. And performing FEM takes 1 to 2 hours for this example, but deep learning takes less than 0.1 second, which means that if we want to optimize something based on stress field and correct phase field, correct propagation, we can utilize deep learning model for really fast exploration of design space. Okay. Yeah. So this is like a role of AI. In terms of predicting something. Now after talking about like a training on AI model, let's try to move utilization of AI model for the design. And what I have recently done in a review paper or guideline paper is I try to categorize the data-driven design problem into 4 cases and try to suggest some representative algorithms. So if we think about a mapping problem, this is, it can be like, if we think about, for example, material design problem, X1, X2 can be like a composition or a property of the source material. And F1, F2 can be like a strength or conductivity, those properties of materials. And what we want to achieve with AI model is try to find this mapping F that connects design space to objective space. And at least from my experience with collaboration with the companies, especially manufacturing companies, it's really hard to secure huge data set like a Google or Apple, Amazon. They can secure like a trillions of data set for the training. But in real manufacturing companies, it's not easy to accumulate such a huge data set. So what I found is that in many engineering applications, it is instead of talking about this fancy word like a diffusion model, like GAN and PIN and CNN, it is more important to think about the essence of the AI, such as whether the mapping is one-to-one or many-to-one, or how densely and widely my training data set occupies the design space, and how expensive is it to collect a data set, and do we have high or low fidelity data sets? So these are like a more important question than like learning the fancy AI algorithm. That's what I somehow found from my experience, personal experience. So one of the category can be like an interpolation-based design problem. This happens when we can secure like a large enough data set and wide enough data set to cover entire design space. Suppose that this red area is the range of the training set. And then if we train AI model for this large and wide and dense data set, it's quite easy to find the target F1, F2, and X1. It's quite easy to find X1 and X2 such that F1 and F2 result. Okay, so this is interpolation problem, and I will get into this details in the third part of today's talk as an Ansys example. And second part of the design problem happens as an extrapolation problem, which is one of the largest bottleneck of AI application. So in gigantic design space, or it's hard to accumulate data set, typically the range of data set is much smaller than design space. Okay, then if we trained our AI model in the limited design space, and it's not easy to find the optimum beyond this range. Okay, for example, if our target is to find this F1 star and F2 star here, out of the AI model trained on this, we cannot find the optimum because there is no guarantee that the accurate prediction for the X1 and X2 beyond this data set. Okay, so if I give you like a one-dimensional schematic, suppose that the input and output relationship is given as black, and suppose also that our training data set is around here as an X. One machine learning model would predict something like this. The other machine learning model would predict something like this, because what they have seen is only these data set. In terms of data prediction accuracy, they are equivalent. However, the optimum found from green model, optimum found from purple model should be different from optimum found in real relationship. And in this case, we have to rely on active learning, reinforcement learning, or advanced neural network architectures. Okay. And because in the limitation of time, I will not gonna get into the detail of those methods. Please refer to the my paper. But if I give you some schematics, whether it's active learning or reinforcement learning, it's like, you know, having some direction toward the optimum and add more the data set and update the machine learning model, as we travel toward the optimum, like optimize and update the machine learning model together. That's what you need for the extrapolation problem. And the third type of problem will be small data set or multi-objective problems. Yeah, one of the most frequent problem is finding the Pareto optimum front, such as maximize both, two or three objects, and they can be often in trade-off relationship. It can be like a production speed and yield, something like that. So in searching for this Pareto optimum front, yeah, we don't need to explore our entire design space. We want to economically and efficiently sample the data set around the Pareto optimal front and around the Pareto optimal solutions, and we can utilize multi-objective Bayesian optimization. It will be handled in fourth chapter of today's talk. And yeah, so this is an example of optimizing toughness and strength and lightweight of the composite materials, and I will show you this in detail in the first chapter. And the fourth category of the problem will be multi-fidelity data set. It can be also shown in many computational engineers. For example, given the same composition and same shape, the simulation, which can be written given as this red mapping, simulation and experiment often has systematic offset. In case of this systematic offset, if we train AI model only with the simulation data set, it will show offset with experimental data. In that case, what can you do? Yeah, we can either use transfer learning or multi-fidelity surrogate model. And today, I will briefly touch upon transfer learning idea. So these are like four categories of data-driven design problems. And I will touch some part of this. And for the details, please refer to the review paper. Now, let's move on to the third part of today's talk, which is deep learning-based design, which is interpolation case. And I will talk about some need from users. Yeah, so as I told you, this is like some sort of a chamber inlet shape optimization with Ansys Fluent, and the problem definition is like this. So what my collaborating company is doing is they are building some ALD coating chamber. They somehow put precursor gas into this inlet, and this precursor gas, move through, these kind of structure, and each of these floors, we have 2 or 3 semiconductor wafers, and on top of the silicon wafer, they want to deposit like a really atomic accuracy coatings. But what they have found is that depending on the locations and depending on the height, they have like a variety of the coating depth. Okay, so what we have done was we run like an Ansys simulation to find the flow distribution within the chamber, and we generate huge data set, and out of this we train the deep learning model to predict flow non-uniformity, and out of this deep learning model we find the optimal design, and finally we are able to design some chamber inlet shape that can generate really uniform flow distribution. So this is like a more detailed problem definition. This is a side view of the chamber. Gas goes in and go out like this. And if we look at from the top, the flow distribution is non-uniform. So what we have done was we defined objective function as flow uniformity, and we construct a deep learning model to predict flow non-uniformity as a function of this size of the hole in the inlet side. Okay, so actually what I found as a user is, Ansys really have like an integrated parametric search one, but it'll be even better if we can utilize deep learning as a surrogate model in the Ansys. But I found that there is a plugin called OptiSlang, but I never used it. But this is one thing, one suggestion that I can have about this. And after training a deep learning model that predict flow non-uniformity as a function of the design variables, yeah, what can you do is, yeah, we can, compare other surrogate models such as GP and polymorphic response surface model with the deep learning model, and we found that, yeah, deep learning model shows better prediction accuracy compared to other models. So in the user's perspective, it will be great if we can have the function of comparing various surrogate models in the Ansys. Okay. And next, what can you do is using constructing this response surface model out of trained deep learning model, we can utilize in a global optimization algorithm such as like a particle swarm method and try to find the optimum out of this response surface. And of course, from the user's perspective, various optimization algorithm can be more smoothly implemented with Ansys. It'll increase the efficiency of users. Okay. Anyway, after going through this cycle, yeah, we are able to find the chamber inlet shape that makes the flow distribution uniform, and this flow uniformity will lead to coating uniformity in ALD coating machine. So yeah, this is work by this guy, and I just share this. I prepared this example for this seminar. Okay, so this is the third part of the talk where we can secure like a large enough data set, and the design space is relatively small. And in performing this, it's quite I would say straightforward. But during this straightforward process, we only use the parametric data generation capability of Ansys, and the other part we have done with our own code. So it'll be really great to integrate everything in more smoother way. Maybe it's already in the Abacus, but we are not aware of. Okay, but anyway, this is one example. Now let's move on to the optimize with costly data set. So in previous example, we are somehow spoiled with huge data set, and we are able to train deep neural network with a large data set. But in many cases, it's not true, because whether it's experiment or simulation, collecting data set is really costly in terms of time and money. So how can we guide an experiment and simulation with multi-objective optimization? So that will be topic of first chapter of today. So let me show you like two representative problem. Yeah, first representative problem will be structural optimization, and this is work by one of my students. And here, the example problem that we chose is try to optimize nature-inspired 3D printed binary composites. Okay, by tuning the aspect ratio and volume fraction and length ratio, or the modulus ratio between blue and the orange, we can tune the toughness and strength and modulus and etc. But we found that although we can analytically write the equations for the modulus in terms of toughness and strength, yeah, we cannot make an analytic functional form, because analytic functional form is not available for the objective function. We cannot utilize gradient-based optimization such as topology optimization. So that's the first issue, which is black box optimization. And also here, the strength and toughness typically have this trade-off relationship. And we also found that whether we run this simulation, whether we do material testing, it costs time and money. Okay, so it's like expensive to accumulate large data sets. So this is one challenges. And the other example I want to show you is process optimization. And and this is an example of injection molding process. Injection molding is a process that is typically used for building like a Lego blocks or like an internal plastic part inside the car. Okay, so this is work by these two guys. So here, what we do is we prepare a mold, and within the mold, we put like a molten plastic. And as this molten plastic solidifies, we keep pressurizing, which is called the packing. And after cooling, we eject this part. In this kind of problem, of course, the production time and the deformation or displacement from this mold shape, they are not available in functional form. And typically, production speed and the deformation, they have in trade-off relationship. And also, it's expensive to accumulate data either in experimental testing or process simulation combining fluid and solid and phase transition. Okay. So here, what you can do is we try to use some surrogate model with uncertainty quantification. So for the typical surrogate model that find the X and Y relationship, yeah, we only have this expectation value, and out of this surrogate model, for the new input, we can predict output like this as a 1 point. However, if you use so-called like a Gaussian process regression or other uncertainty quantification, in addition to this expectation value, we can also quantify the uncertainty, and this uncertainty becomes large as as the data is further from the already measured data point, like here and here and here. And given this uncertainty information, in addition to expectation value, we can also have the information about its accuracy or standard deviation. And out of this, we can somehow suggest and recommend the next experiment. So this is the like an example of Bayesian optimization. So the ground truth is this is input and this is output. Ground truth is red, and suppose that we only have 3 data point. Yeah, data point 1, 2, and 3. And out of this 3 data point, what surrogate model suggests is this black line. And after suggesting this expected line, it also quantifies the uncertainty like this gray area. Okay. And because of this uncertainty and the expectation value are available together, yeah, we can suggest next experiment with the point with the largest uncertainty, or the next experiment with the point with largest expected improvement. Okay, so for example, the largest value until now is here. So we have some order of improving the output, yeah, within this area, right? If we put new experiment here, we don't have any probability of improving the data set. So by combining this expected improvement and uncertainty, we can suggest next experiment, which is called expected improvement. And based on this expected improvement or acquisition function, we perform next experiment, and then expected improvement will be updated. And according to this suggestion, we perform next experiment or simulation, and we keep doing this. And then we somehow optimize and regress in simultaneously. Okay? So this is the idea of Bayesian optimization. So we can either use expected improvement or probability improvement for the single objective optimization. And we can also extend this to multi-objective optimization to find the Pareto optimum front. Okay? For the two objective problems, instead of finding just the expected improvement or probability of improvement, we can define sort of hypervolume such that we can think about expected hypervolume improvement or probability of hypervolume improvement to search for our next data set. So what we can do is we can perform costly experiment or simulation according to the suggestion of this MBO. So in simulation side, what we can do is we can implement this entire MBO into the macro program. And this is an example in Abacus implementation. And actually in material science and chemical engineering, human experiments are now replaced by robot arms. Okay, we have robot arms, and robot arms fabricates like photovoltaic cells or doing organic chemistry experiment instead of a human. And this robotic arm is controlled by an MBO algorithm. Okay, according to the MBO, it mixes the materials and process the material and generate prototype devices. Okay, so today I'm gonna show you, of course, yeah, this kind of example and a little bit of human experiment example. So the problem I will show you today is trying to optimize the shape of 3D printed composites. Okay, and here the toughness and strength and light weight under the trade-off relationship. And here, the design variables are like a three geometry design variable, such as aspect ratio and the thickness ratio and length ratio. And there is material design variable, which is the ratio between aspect elastic modulus between blue and orange. And we're gonna have three objective functions. Okay, so what you're gonna do is by tuning these four variables, we'll try to find the Pareto surface out of these three variables in trade-off relationship. So as a first case, we can do experiments and we just guide the experiment run by a human being. So this is my student's work. So he generates several pieces out of a 3D printer and measures stress strain curve. And yeah, this MBO suggests next 3D printed sample. So he generates 3D printing sample according to the MBO suggestion, and he keep generating this process until the toughness keep increasing. So this kind of a single objective experiment can be done by human being. And then to move on to the more complex one, we do better couple robotic arms with MBO algorithm to do all of this in automatically. And there are several national labs in Korea doing this kind of stuff with robotic arms now. And then as a second way is we can solve the MBO multi-objective optimization with FEM and do experimental validation later. And we have a fully integrated Abacus Python macro with this MBO algorithm. So this algorithm, this Python macro automatically runs Abacus and change the shape according to the suggestion of the MBO algorithm and do the find the optimum automatically. So yeah, so the example is as follows. Yeah, so in terms of strength and toughness, trade-off relationship, and Pareto optimum search, yeah, the Abacus keep generating the data set, about more than 100 data set to find this Pareto optimum. And if we search for the designs along this Pareto optimum, yeah, we see what we need to change to tune the strength and toughness within the Pareto optimum, because we cannot optimize strength and toughness together. We cannot achieve this way. However, within the Pareto optimum, yeah, at least this kind of simulation suggests us what's the critical design variables. And we can do something similar for the strength and lightweight design and toughness and lightweight design. And we can see that like what are the critical variables to tune the toughness and lightweight and strength and lightweight, and all of these are found by Abacus automatically when we implement MBO in its macro program. And yeah, and without having any background in the mechanics, if one can do like Abacus macro and the MBO algorithm very well, he can generate like these kind of material property target and its design with Abacus simulation. Okay, and of course, after searching for the Pareto surface out of the toughness, strength, and specific volume, yeah, we can generate real samples with 3D printers, and we do simulations, and we found that our FEM and MBO driven design actually matches with experimental result. Okay? And one thing I also want to share today is if we compare the MBO acquisition function EHVI and PHVI with conventional NSGI2, what I want to say share is, in terms of finding the data set near the Pareto front, they outperforms the conventional algorithm because EHVI and PHVI, they also include the information about uncertainty. Okay, so based on those probabilistic information, they are like more efficient to search the data set near Pareto optimum. And if we somehow see the error or shortest distance to the Pareto front compared to the NSGA, which is gray, the green and blue, which is the MBO acquisition function, shows much lower error or distance to the Pareto front. In terms of distribution metric, distribution metric means that like a uniform and wider Pareto front search. You can see that EHBI and PHBI outperforms NSGA. Okay, so in somehow guiding costly experiments or costly simulation, utilizing and implementing MBO would be would enable us to efficiently search for the Pareto optimum. And I think, yeah, because I can implement this in the Abacus, in the Ansys, if we can implement and integrate this MBO in the Ansys, it will be easier for users to find the design task they want to do. Okay, so this is some example. And second example is like injection molding process optimization. As I told you, this is quite complex process engineering, and actually it requires like a lot of experience. Okay, so and as I told you, it's quite similar to the structural optimization that I showed you. So until now, this optimal process condition has been intuitively determined by field experts with many years of experience. And at least in Korea, there is no systematic way of optimizing process parameters. And what are the process parameters? It can be about like more than 10. It can be mold temperature, filling speed, and resin melt temperature, and packing pressure. Packing is done like to compensate the volume shrinkage during the solidification. So we can do packing in this kind of multi-step. Okay, and the output we want to achieve is the production time and deformation from the mold. Okay, and our plan was test MBO with completely simulation data set first, and then we want to move on to the real company. So this is ongoing, and simulation we have done and we have made the success. So at least for the small sample with 1 feet length, we found that after MBO, the optimal packing profile was single stage. And for the larger sample with 3 feet diameter, this is air conditioner fan part. Okay, after MBO, we find that two-stage packing pressure is optimum packing profile. And regarding like an even larger part, 6-pin length bumper part, we found that like a 3-stage packing is necessary to have fast production time and small deflection. And we found that this is consistent with field engineers' intuition and experience. And without getting any help from the expert in the field, computer algorithm was automatically able to find this process parameters. Okay, so these are some examples of combining like a experiment and simulation guiding algorithm into the computational tool, and I think Ansys can have this kind of complementary or supplementary tool in their software, and maybe it's already there. So, and the last part, let me briefly touch down to homogenization theory. This is like typical scale bridging scheme for the particulate reinforced composites. So the entire holistic view is something like this. Suppose that we make some part out of nanocomposites or microcomposites having nanoscale or microscale inclusions. And what we can do is we can construct constitutification out of atomistic modeling or FEM-based RV modeling and combining homogenization theory. And after we construct this constitutification, it can be input as the macro scale simulation. And one of the best players in this business is, I think, the DigiMat software. And DigiMat can offer the DigiMat mean field theory. So what DigiMat mean field theory offers is, given various shape and orientation distribution of this inclusion, it somehow construct the constitutification, and this constitutification can be plugged into macro scale FEM continuum simulation with the failure criterion like this. Okay. So what we can do is, this is a work by these alumni students. We can somehow provide a more sophisticated version of DigiMat MF, which is constitutive equation provider, and there is a review, and these are the extensions. So if I give you the basic concept, yeah, if the volume fraction of inclusion is too large, it's quite hard to make analytical theory. However, if it's low volume fraction, the strain field inside the inclusion is uniform. Okay. After having this observation, if we compare this uniform strain distribution inside, it can be same as a single inclusion strain distribution. Okay. And if we somehow have the relationship between the external stress and internal stress relationship using the T stress tensor, and then we can predict the relationship between external stress and the internal stress using concentration tensor A. Okay, this A will be given as a function of T and the volume fraction. And the concern is it's not easy to find this T tensor, and there has been the work by Professor Ashby like many years ago, like more than 60 years ago. And this T tensor can be obtained by single inclusion problem with some eigenstrain. And because we are considering like a same modulus in the entire domain, we can utilize Green's function and we can write down T in terms of shape of the inclusion and the Ashby tensor. So this is the basics of the theory. And instead of circular inclusion, if we have like a graphene or nanowire, we can use oblate or prolate ellipsoid as on like HLB tensors. So what our model outperforms the current DGMAT software is following extension to various physical property, interfacial imperfection, and complex loadings. So, in terms of various physical properties, electrostatics and mechanics and electrostatics, they are like mathematically analogous. We can extend it to variety of physics, and we can predict, various physical properties using more like a universal equation. That's what we can do. And then if we consider like a micro scale or nanoscale inclusions, we have to concern about this interface imperfections such as a displacement jump and the another third phase formation interface. In this kind of modeling, our model, our lab also developed quite nice models in terms of displacement jump in elasticity. And in conduction problem, we implemented the temperature jump, which is capture resistance, and other physics. We have implemented these and derived the correct HLB tensor and effective modulus, effective conductivity, considering this interface. And then regarding the cyclic and complex loading, whether we have this loading and unloading cycle many times, whether we have complex loading in X, no loading in Y, and loading in Y, and the unloading in X, everything is combined. Even for this complex loading, our model can provide a variety of nice predictions. Okay, but I think these are the three areas that our model can outperform DGMAT, and it can be also used as one of the scale bridging tool in Ansys, I think. And however, what I want to tell you is this is like a mean field approximation, analytical approximation, and deviates in some conditions. To complement to this, what we can do is we can generate huge data set out of analytical homogenization theory, and we can train deep neural network with huge data set. And after training deep neural network, we can tune the prediction of a neural network with small and accurate data sets, such as 5-mesh FEM. Okay, we call this as transfer learning. And then this network, although they see small 5-mesh FEM data set, they can predict finer mesh FEM result very well. So this is one way of combining deep learning and conventional homogenization theory and FEM all the way together. And this is the result comparing the stress strain curve. The circles are FEM data, and red is the transfer learning, and blue is the result only trained with FEM without utilizing the homogenization data. Because typically, if we have a small data set for deep learning, it prone to overfit the data, so its prediction accuracy is not that great. So this is the result. Okay, so I think I've spent almost 45 minutes. So to summarize this talk, I suggest strategic data-driven design category strategies in 4 categories, and then I shared a deep learning-based optimization with interpolation and suggest a few things as a user's perspective. And I also introduced the concept of multi-objective Bayesian optimization for guiding costly experiments and simulation. And in the last part, I talk about a homogenization scheme for scale bridging, nanoscale particle reinforced composite or microscale particle reinforced composite. And before end of the talk, I'd like to thank the Ansys again, and also thank the financial support from NRF Korea and Hyundai Heavy Industry Group. Yeah, thank you very much for your attention.